everybody, it's Miss Manili, and I'm going to go through the second semester final exam review guide for Algebra 2. Most of the final exam is going to focus on what we've done fourth quarter with periodic functions and rational functions, but you'll find that there's still some references to like normal distributions in statistical analysis, and some other things that we've done earlier in the semester. The first section is the non-calculator section, and then we have another calculator section as well. I've tried to divvy up the review guide to follow along with which questions on the exam are calculator based and which are not. So everything in the first part of the review guide are things that you're going to have to do without a calculator. So make sure that you understand how to set these problems up and solve them without a calculator. The math itself is pretty straightforward. You shouldn't really have to worry about like long division or multiplying by like values that have three decimal places. But let's go ahead and take a look at the first problem. It says, given that the cosine of theta is equal to 4 over 5 and that theta lies in the fourth quadrant, determine the value of the sine of theta. Well, if I look on my unit circle, I can see that the cosine is never equal to 4 over 5. If I look at the ordered pairs, the x values on my unit circle are either 1/2, the square root of 3 over 2, the square root of 2 over 2, 0, or 1. Like they're never 4 over 5. So I can't use the unit circle to help me identify theta. Instead, we have to draw a triangle. And if I draw a right triangle, let's call this angle theta. This would be my right angle. And so if I know that the cosine is 4 over 5, I want to think about my SOHCAHTOA relationship. And remember what SOHCAHTOA stands for. The SOH is your sine is equal to the opposite over the hypotenuse. The second part of that is that the cosine of theta is equal to the adjacent over the hypotenuse. And I have a fraction that is equivalent to the cosine of theta. So that means that my adjacent side I can identify as 4, and my hypotenuse I can identify as 5. And so then what I'm going to do is I'm going to simply label my right triangle according to this information. So if this is theta, if this is my angle, the adjacent side means the side right next to it. And we do have two sides next to theta, but this side is my hypotenuse. And I know that that is equivalent to 5. So the other side is considered my adjacent side, and I know that is equal to 4. My opposite side is the one that is unknown, and I have to figure that out. But fortunately, we have a formula that enables us to relate the sides, the lengths of the sides of a triangle, and that's called the Pythagorean theorem. The Pythagorean theorem basically says that a squared plus b squared is equal to c squared, where c is the length of your hypotenuse. So if I know that my adjacent side, I'll call that a. So 4 squared plus b squared, I don't know what that is, has to equal 5 squared. Or, basically, that 16 plus b squared is equal to 25. And if I subtract 16 from both sides, I find that b squared is equal to 9. Now remember, that is my opposite side squared. So if I want to find the length of my opposite side, I have to take the square root of that. And so I get that b is equal to 3. So my opposite side has a length of 3. And this is actually one of your special right triangles. The 3, 4, 5 triangle is one of the special right triangles that you guys learned about in geometry. Now that I have my triangle set up, I want to determine the value of the sine of theta. And so I know, according to my SOHCAHTOA relationship again, that my SO, this statement here, tells me that the sine of theta is equal to my opposite over my hypotenuse. And so that means that the sine of theta must equal, well, my opposite side we said is 3, and the hypotenuse we said is 5. So the sine of theta must equal 3 over 5. But I have another piece of information that I need to consider, and that's that theta is in the fourth quadrant. So if you think about your unit circle, we have quadrant 1, 2, 3, and 4. And if theta is in quadrant 4, then my coordinates, if I think about the point that would be associated with my cosine and sine, or with x and y, the x value is positive, and the y value in this quadrant is negative. And so that means that the sine of theta must be negative because it's in the fourth quadrant. And on the unit circle that you have, which you'll be allowed to use on the exam, it tells you in each of the quadrants what functions are positive and what functions are negative. So my final answer here is going to be the sine of theta is equal to negative 3/5. Now this type of question was on your third quarter quarterly. So this is a question that you've seen before. It was one that I think performance probably wasn't as good as it was in the past. In number 2, it says consider the graph of the periodic function below. It's actually to the right, but you get what I mean. And it says to state the equation of the midline. Remember, the midline is going to be that imaginary line that cuts through that graph so that the max and the min are exactly the same distance from that midline. And so I can see that that occurs when y is equal to negative 2. Since it's a horizontal line, it's going to be of the form y equals. Letter B asks about the amplitude. Well, the amplitude is going to be whatever the distance is from my midline to my max. Or I could also do the same thing from my midline to my min. It's going to be the same distance either way. And you can simply count the blocks. So 1, 2, 3, 4. So my amplitude is 4. And then it asks about the length of the period or cycle. So most of the graphs that we've done, where we've actually plotted the graph or we've come up with the equation of the graph, we've used a period of 2 pi. But if you remember, on those graphs, my x-axis was scaled by pi's. So you'd see pi over 6 or pi over 4. In this case, you don't. You just see the numbers negative 4 to positive 4. So my period's going to look a little bit different. But by definition, a period is simply the length of a cycle. And so it doesn't really matter where you decide to make the cycle start as long as you end in the same spot. So for example, if I want to say that this point corresponds to the beginning of my cycle, then this point, because that's when it returns to the max, would be the end of my cycle. And I can essentially estimate how many spaces are between those two maximum values. It's a little bit hard to see here because my maximums don't occur at even values of x or at exact values of x, but I do notice that my midline intersects my graph very evenly. And so again, I'm looking to see how long it takes to complete one cycle. So if I call this point my starting point, even though the graph passes through it once, that would be my ending point. And again, I can just count how many spaces. So 1, 2, 3, 4, 5, 6. So the period in this case is simply 6. I don't have to put a pi next to it because it doesn't tell us on the x-axis that it's scaled that way. So my period is simply 6. Okay? In number 3, you're asked to simplify each expression. One of the things we talked about was the Pythagorean theorem, where a squared plus b squared is equal to c squared. And if you think about the unit circle, we created some triangles or some angles on that unit circle. And we basically said that the x-coordinate of this point for any of the given points is going to correspond, if this is theta, to the cosine of theta. Oops. Let me fix that. And the y-coordinate is going to correspond to the sine of theta. We also know that on the unit circle, my hypotenuse is 1. So if I kind of look at this triangle a little bit differently, another way of saying that is that my adjacent side corresponds to the cosine of theta, and my opposite side is going to correspond to the sine of theta if the hypotenuse is 1. And so if I think about what is sine squared plus cosine squared, well, if I think about now labeling my adjacent side as the cosine and my opposite side as the sine, then I can tell from my problem here that the cosine squared plus the sine squared, since I'm talking about the legs of my triangle, of my right triangle, that's going to have to equal 1 squared. Or if I just kind of put the order back, I can say that the sine of theta squared plus the cosine squared is going to equal 1. This is called our Pythagorean identity. We didn't really do a lot with this, but for those of you that may go on to pre-calc, you'll use this identity to solve equations. So it's important that you know how to manipulate and rearrange equations involving different trig functions. So in letter B, again, we're trying to simplify this expression. The one thing I notice is that I'm dealing with cosine and tangent. Well, tangent can be rewritten using sine and cosine. If you remember, the tangent of theta is equal to the sine of theta over the cosine of theta. So if I'm dealing with the tangent squared of theta, that's simply going to be the sine squared of theta over the cosine squared of theta. And if I bring everything else down, my cosine squared theta and my cosine squared theta over here, then if there's anything that can be canceled or reduced, I can do it at this point. And what I notice in this part of the equation, or this part of the expression, is that I've got a cosine squared in the denominator of a fraction, and I'm multiplying it by a cosine squared. Well, if you think about it, that's just over 1. And when I'm multiplying and I have items that are on the numerator and the denominator that are the same, I can actually cancel them. And so now what I have is the cosine squared of theta plus the sine squared of theta. And this goes back to what we just did in letter A. When I add those two things together, I get 1. Okay. Number 4. These are graphs of functions. We're going to first look at a graph of a rational function. And this is something that we saw at the beginning. I think we were in our polynomial unit when we looked at transformations of all sorts of different functions. And the one that we're going to talk about in number 4 is what we call a rational function. It still follows the same format of a, h, and k, where we have a times 1 over x minus h, and then a plus k on the outside. The h and the k values are going to correspond to your asymptotes. And so you can see from this graph that both sides of the graph seem to be approaching this vertical line. And both parts of the graph seem to be approaching this horizontal line. Those are our horizontal and vertical asymptotes. This point where those two asymptotes intersect are going to correspond to your h and k value, because that's how the graph has been shifted over and up. And since the coordinates here are 2 and 1, the 2 is going to correspond to your h value, and the 1 is going to correspond to a. And that's probably, to k. That's probably the easiest way to consider this function. So in letter A, it says, how many times would the graph of g of x, which is equivalent to the square root of x plus 2, intersect the graph of f of x? Well, I've got to think about what g of x looks like. If I'm dealing with a square root function, if you remember, y equals the square root of x is simply, it's a half a parabola on its side. So if I'm adding 2 to the square root of x, because that's a k value, I would shift the graph up 2 units. So instead of having the critical value at the origin, I'm going to shift it up so it has a y-intercept of 2. And think about graphing. How many times is it going to cross f of x? Well, it just crosses it 1 time. Let me try a different color. So in letter B, now we're looking at the square root of x minus 2. So again, I'm going to take my parent function, but this time I'm going to shift it down 2 units. And when I do that, how many times is across the graph? And because the graph has 2 parts to it, I have to consider every single time the square root of x minus 2 crosses f of x. And I can see very clearly that it crosses 2 times. So the next question becomes, which of the following aren't going to cross the graph of f of x? So if I think about my function, which is, I wonder if I can, let me draw my parent function here in black. That's what my parent function is going to look like. So if I'm thinking, and I should be able to move this with my finger. Yep, perfect. So in letter I, or the first Roman numeral, it's asking me to consider the graph of the square root of x minus 2. Remember though, since, since the minus 2 is underneath the radical, I'm actually shifting it in the opposite direction. So it's going to shift to the right 2 units. And so if I see the shift, sorry, my finger's a little unsteady. If I see that shift, does that cross f of x? And I think it's pretty obvious that it does. So this is not going to be one of my answer choices. let's go ahead and move my my g of x function back. So let's think about the function g of x where it is equivalent to the square root of x minus 4 minus 2. And again, that x minus 4 means my graph is going to shift 4 units to the right, and then we also want to shift it down 2 units. There we go. All right. And remember, this graph continues on and on and on forever and ever and ever. So my graph of f of x, whoops, my graph of f of x is going to keep going. And so if you look at it that way, again, I think you can see that the two graphs do in fact intersect. So this is not going to be one of my answer choices. So let's move my parent function back. Okay. Now we're looking at the square root of x minus 4 plus 2. So if I move it over 4 units and go up 2, look at that. Does my graph actually intersect with f of x? And the answer is no. That graph is going to continue, f of x is going to continue to approach both of those asymptotes. It's never going to increase so that it could hit g of x. So number 3 doesn't cross f of x at all. So that's one of my solutions. If I think about the next one, let me go ahead and move my parent function back. G of x is equal to a negative square root of x minus 2. So since the x minus 2, since that minus 2 is under the radical, I'm actually going to move my graph to the right 2 units. But I have to note that since there's a negative in front, I also have to flip my function. So it should look like that. And I think you can see very clearly it is never going to intersect f of x. So this is another solution, or another answer to the question. And then finally, number 5, let me go ahead and move this back. Okay, so there's my parent function. So in number 5, it's asking me to consider the square root of x plus 4 plus 2. And so plus 4, oops, plus 4, sorry, is going to actually move to the left 4 units. Oops. And up 2 is going to put me right there. And I think you can see that my two graphs will in fact intersect, so that is not going to be an option. Oops. Okay. So the only correct responses there would be options 3 and 4. Okay, and number 5, we're talking about the transformations of functions. We've been doing this all year. We have our a, our h, and our k. Let's follow the order of operations, and according to our order of operations, we'd first look at the quantity within the radical or inside the parentheses. And I see an x plus 5. Well, that 5 is going to correspond to h. And in this case, my h would correspond to a negative 5 because it's always opposite. And that tells me that f of x is shifted left 5 units. Now I'm going to work my way out of that quantity, and I'm going to look at that negative 1/2 that's being multiplied. The negative tells me that the graph is going to be reflected vertically. And the 1/2 is going to tell me that it is going to be compressed vertically, because that number is less than 1. So that takes care of my h. And then the very last thing I can do is talk about my k value, which is negative 3. And that tells me that my graph is going to be shifted down 3 units. Okay? In letter B, we're talking about a sine function. And this time we're calling it g of x. So the same transformations apply. I'm going to work on the inside out. So I'm going to say g of x is shifted. And this time, because there's a negative inside my parentheses, I'm actually going to shift the graph right 5 pi over 6 units. I'll work my way out using my order of operations. Multiplication would come next. And so because that 3 is greater than 1, I'm going to say that it is stretched vertically. And then finally, I can deal with my 1 and say that it is shifted up 1 unit. And that is how you would describe the transformations of each of these two functions. Okay. In number 6, it says to complete the table below to describe each function's characteristics. So the domain, remember, is referring to the x values. We're also looking at the distinct number of real roots, and in this case, those are going to correspond to our x-intercepts if they are real. And so what we need to do is consider each of the functions that were given to answer these questions. And I think that it really helps to consider what the graph of these functions would look like. You were also given some characteristics about these functions that I think it would help to study. So the domain, we know that a sine function is going to be a wave that goes on forever and ever and ever and ever. So the domain is going to be all real numbers. I can take the domain, I can take the sine of anything. Now, how many times is this thing going to cross the x-axis? Well, it could happen infinite many times because I've got a wave pattern and it never stops. Or it may not happen at all. And that's going to depend on two things. It's going to depend on how big my amplitude is, and also where my midline occurs. So if I think about where this is, and I'm just going to sketch this graph, I've got a midline at positive 1, and I have an amplitude of 3. So my graph is going to have to cross the x-axis. And because a sine function goes on and on forever and ever and ever, it's going to cross the x-axis an infinite number of times. But you do have to be careful because it's possible to have a sine function that never crosses the x-axis. All right. In letter G, this is one you have to be careful of. This is a root function, a square root function. And square root functions, think about the graph. If this is the square root of x minus 4 plus 2, if I think about this, x minus 4 is going to actually mean that I have to move my cursor to the right 4 units and up 2. And that's what my graph is going to look like. Once I know what the graph looks like, I think it makes it really obvious that my domain cannot be all real numbers. I can't take the square root of a negative number, so I only have values that are above 4. And so I basically, and one way to do this is to simply take what is underneath the radical, because if I'm taking the square root of something, it has to be positive. So it has to be that x minus 4 is greater than or equal to 0, because that would guarantee that my domain is positive. And then I can simply solve this inequality and get that x has to be greater than or equal to 4. And this is the domain of my function. And I can see that on the graph. It doesn't go to the left of that point. Now that I've graphed it, I can also see how many zeros this function is going to have. Since it starts so far above the x-axis and never changes direction, this function has no real zeros. H of x, we've got x minus 2 times the quantity x plus 3. Hopefully you guys recognize that this is quadratic or binomial. Well, I'm actually going to leave. I'm multiplying two binomials. But this is a quadratic function. And that basically means that my domain has to be all real numbers. And the number of distinct zeros, remember, if I just let h of x equal 0 and I solve, and I can actually do this for all of them, it's just some of them it's not that easy. If I set those factors equal to 0, I will find that x is equal to 1 and x is equal to negative 3. So I know that there are 2 roots to this function, or 2 zeros to this function. And you're not going to be asked to solve them, you're just going to be asked to state the number of zeros that the function will have. H of x is another one. We have a power of 2. which is just like h of x, except it's in a different format, but they're both quadratic. We've got negative x squared minus 2, and I want to know the domain. Well, for all quadratic functions, the domain is going to be all real numbers. If I want to know the distinct number of zeros, then I'm going to have to imagine what this looks like. So I know x squared is my parent function, but it's being shifted down and it's flipped. So it actually is going to look something like this. It's a parabola that opens down below the x-axis. And so this is not going to have any zeros. In letter L of x, these are both rational functions that are showing up in L and P. And what we want to do is we want to factor and cancel. Both of these expressions, or at least L of x has been factored for you. And I notice that I've got these two quantities that are both equivalent to x plus 1, which means I can cancel them out. But if I've canceled them out, that doesn't necessarily eliminate them from the problem. It just becomes a little bit hidden. So x minus 4 times the quantity x plus 1 divided by x plus 1. Since these two values cancel, I know that this value down here cannot equal 0. If I've got a fraction, I know my denominator cannot equal 0. So what I'd want to do is I just want to say x plus 1 cannot equal 0. And then I can solve for x. If I subtract 1 from both sides, I get that x cannot equal 1. And when I'm talking about the number of distinct zeros, or the number of x-intercepts, since this quantity canceled, I'm just left with x minus 4 on top. Since that's a factor, it's going to correspond to a root of x equals 4. So that tells me that there is one real root for that function. P of x. This time our equation is not given to us in factored form. So the first thing we want to do is see if it's possible to simplify it. So I'm going to look at my trinomial, my x squared minus 4x minus 12. I'm going to think about my product and my sum. My product is always a times c. In this case, that'll be negative 12. And my sum is negative 4. And I'm thinking about what numbers will multiply to give me negative 12 and add to give me negative 4. That's going to be negative 6 times 2. And so when I factor this, it's going to ultimately be, actually give myself a little bit more space. We'll have, let's see, x minus 6 times x plus 2 on top. And then on the bottom, we'll have an x plus 3. And unfortunately, nothing cancels. So when I'm asked to define my, or when I'm asked to state the domain, I know the domain is going to occur everywhere x exists. Well, if I have a denominator in my fraction that involves a variable, I have to make sure that it doesn't equal 0. So I'm actually just going to write x plus 3 cannot equal 0. Because then otherwise I wouldn't be able to divide by 0 and I wouldn't be able to do anything with my function. So if I go ahead and solve this equation, I'm going to get that x is equal to negative 3. And that's going to be what my function is not allowed to be. So remember how I use the not equal to here? My function, or my value of x is not allowed to be negative 3, because that would make my denominator 0, and I can't divide by 0. Okay. It also asks how many zeros there are to the function. Well, my function is going to be 0 anytime my numerator is 0. And so if I let x minus 6 equal 0 and x plus 2 equals 0, I can determine my zeros, or the x-intercepts of my function. So if I add 6 to both sides, I get that x equals 6. On the other one, if I subtract 2, I get x is equal to negative 2. That tells me that there are 2 real roots to this function. Okay, in the next table, you're asked to describe some characteristics of rational functions per se. So rational functions have things called wholes. They have vertical and horizontal asymptotes. They also have x-intercepts. And so on your final exam, you're going to be asked to identify some of these characteristics. Each of the functions is factored for you. So basically, to find a whole, you want to see what factors cancel. And so if I take a look at my first one, x plus 1 on the numerator and denominator both cancel. So what I do is I say, all right, so x plus 1 cannot equal 0. I'm sorry, I don't want to say cannot equal 0. I'm just going to say if we let x plus 1 equal 0 and solve for x, that tells me that x equals negative 1 is a whole. That since there's nothing else left in the denominator, I don't have any vertical asymptotes. And then I just have to look at my numerator again to see if there's any way that my numerator can be 0. And since I still have that factor of x minus 4, if I set that equal to 0, I find that x equals 4 is one of my intercepts. So there is one possible intercept. In letter G, to find my wholes, I'm looking to see what cancels. Both of these quantities cancel, that x plus 1. So if I set x plus 1 equal to 0, again, I find that I have a whole at negative 1. Notice how this time I do have a quantity in my denominator. So I want to make sure for a vertical asymptote that I set my denominator equal to 0. And so what's left after I've canceled is x plus 2. And if I set that equal to 0, I get that x equals negative 2 is my vertical asymptote. The x-intercept is again going to occur wherever my numerator equals 0. And again, since I've already canceled those x plus 1s, I don't have to worry about it. So I'm going to set x minus 4 equal to 0. And again, I get that x is equal to 4. So there is 1, 0 for this function. In letter H, I've just got 1 over the quantity x minus 2. Since nothing cancels, I don't have any wholes. To find my vertical asymptote, I want to set my denominator equal to 0. So x minus 2 equals 0. If I solve for x, I get that x is equal to 2. And my x-intercepts occur when my numerator is equal to 0. Well, is there any way for 1 to equal 0? No. So I have no x-intercepts. This function is not going to cross the x-axis. The letter h of x, we're going to go through the whole process. Let's see if anything cancels. I've got an x plus 2. In fact, I've got two x plus 2s. Let me write it twice. So I've got x plus 2, the quantity squared on top, and then x minus 3 and x plus 2 in the bottom. That makes it so one of those x plus 2 quantities cancels out, and that leaves me with a whole. So I'm going to set x plus 2 equal to 0, and when I solve, I get that x is equal to negative 2. My vertical asymptote, again, is going to occur when whatever is left in my denominator is set equal to 0. So if we have x minus 3 equals 0, my vertical asymptote occurs when x equals a positive 3. And if I think about whatever's left in my numerator, that's going to help me with my intercepts. But I have to be really careful here, because if I look at that x plus 2 in my numerator, it's tempting to say then that x equals negative 2 is an x-intercept. Problem is, I've already identified x equals negative 2 as a hole in the graph. So if there's a hole in the graph, that point does not exist on my function. So it can't be my x-intercept. So because negative 2 is a hole, it can't be a 0. Okay? So there would be no x-intercepts for that one. Okay, let's take a look at number 8. Here you are given the graph of a rational function. So when you see something like this, that almost looks like a target, that is the hole. The asymptotes don't show up because they really aren't part of the graph, but if you think about the lines where the graphs approach, so I can see that there appears to be a vertical asymptote here where both sides of my graph are approaching that line, but they're never touching or crossing it. Looks like I also have an asymptote here because both graphs are approaching that horizontal line. So that gives me a little bit of an understanding about the different pieces to this graph. This question is asking me to determine the interval that describes the domain of the function. So I want to describe all of the possible x values. And so my x values are going to get split up because of the asymptotes and because of the holes. And so there's actually going to be 3 parts to my domain, because I've got this section of my graph here, and that's going to go on forever and ever and ever. It's going to go up forever and ever and ever, but it's never going to cross -3. So that basically tells me that my value has to be less than -3. So on this part, x is less than -3. Well, I've also got this piece here. And again, that's going to go straight down, and it'll get closer to -3, but it's never going to touch it or cross it. And it stops here. So another section of my graph goes from -3 to +2. And it doesn't actually intersect with -3 or +2 because the function doesn't exist at those values. So my inequalities don't have an equal sign. And then I have this piece here, which basically goes from 2 on. Or another way of saying it, x is greater than 2. And again, I'm not putting an equal sign anywhere because my function doesn't actually exist at -3 or 2. So I can see now that there are 3 sections to my domain. There are 3 areas on this graph that x can be a part of. But notice that your answer choices are all written in set notation. And so if I'm saying that x is less than -3, how about if we look at this from a number line perspective? So if this is -3, -2, -1, 0, 1, and 2, if I think about this from a number line perspective, I'm basically saying it can't equal 3, but it can be anything less than 3. It can also be anything between -3 and 2 without being 3 or 2. And then it can be anything above this. So when I think about my domain, over here is -infinity. Over here is +infinity. So my first set for my domain is going to be from -infinity to -3. So -infinity to -3. But it can't actually equal either of those numbers, so we use those open brackets because that means that the function can't actually equal -3 or -infinity. And then I've got this segment here from -3 to 2. Same thing, the function doesn't actually equal -3 or 2. It's between them, but it doesn't actually equal them. And then that last section where my function is greater than 2, meaning that it goes from 2 to infinity. And again, each piece of these, my function cannot exist at -3 or 2, so I'm using these open brackets. When I put it all together, it becomes a union. And that's what that symbol means if you remember from our probability unit. Okay, and so that's going to correspond to number 5. Okay. Numbers 9 and 10 deal with our rational exponents and radical expressions, properties, and solving equations. So in number 9, you're asked to solve each expression, simplify each expression. So in letter A, we have a product, 2 times x to the 5th times y to the 6th, that we're raising to the 3rd power. Because I'm multiplying all of my terms inside the parentheses, I can actually distribute my exponent to each term. Be careful that you distribute it to the number as well, because this is going to transform into 2 cubed times x to the 5th cubed times y to the 6th cubed. And 2 cubed, if you use your table, is 8. When I want to simplify the other expressions, I need to refer to another property, though. We've got a power to a power. And a power to a power means that I need to multiply my exponents. So this is going to leave me with x to the 15th power and y to the 18th power. I can do the same thing when I have a rational exponent. I'm going to distribute it to each of these terms. So I'm going to have 81 to the 1/2 times x to the 5th to the 1/2 times y to the 6th to the 1/2. Well, 81 to the 1/2, remember the 1/2 power is really just the square root. Square root of 81 is 9. With those exponents, I need to multiply them since I'm doing a power to a power, and 5 times 1/2 is simply 5/2. And if I'm thinking about my powers of y, 6 to the 1/2, or y to the 6th to the 1/2, I'm going to multiply 6 times 1/2, and that gives me 3. In letter C, we're looking at a radical expression where I'm taking the fourth root of 81, x to the 8th, y to the 3rd. Another way to write this, if you're more comfortable, would be to say, all right, well, this is 81, x to the 8th, y to the 3rd. The whole quantity is being raised to the 1/4 power. And remember, the 1/4 power is the same as the fourth root. And because I'm multiplying, I can distribute this to each term. And 81 to the 1/4, we're going to have x to the 8th to the 1/4, y cubed to the 1/4. And then I need to simplify. 81 to the 1/4, or the fourth root of 81, is the same thing as taking the square root of 81 twice. And so if I do that, I end up with 3. You can also use your table to figure that out. If I've got x to the 8th and the 1/4, I need to multiply 8 times 1/4, and that's going to give me x squared. And if I multiply for y, 3 times 1/4, that's going to give me y to the 3/4. Okay, the last section in the non-calculator part of the review deals with solving equations. And there are several different types of equations. We've got radical equations, we've got equations that involve rational exponents, and we have rational equations. When it comes to solving the radical and rational equations, there are two things you need to check when you're dealing with powers and roots. When you have an even power, let me write this down. When you have an even power and you solve that equation, you've got to remember, for example, if I have x squared is equal to 4, I know I'm going to use the square root to solve, but I need to remember that 4 actually has 2 roots. So I'm going to need to remember to put a plus or minus with my answer when I take an even root. So if it starts off with an even power, I've got to remember to put the plus or minus with my answer. So let's take a look at the 4 choices. In letter A, it's the cube root of x minus 3, so that's not an even root. But if I take a look, or I'm sorry, an even power. If I take a look at letter B, x is being raised to the 2/3. The number on top corresponds to the power. And since that's even, I need to remember when I solve to include both roots in my answer. Letter C is a rational function, which I'm going to solve a little bit differently. In letter D, this is the square root. When we're dealing with square roots, we also have to be careful. So if I have an even root, what I need to look out for is something like this, where I have the square root of x is equal to, let's say, -1. If I square both sides to undo my square root, I can do that, right? The square root of x squared, those two, the square and the square root, are going to cancel each other. Make sure when you're simplifying the -1 squared that the -1 is in parentheses, and you're going to ultimately end up with 1 because -1 times -1 is going to be positive. But if you think about it, the square root of 1 is not equal to -1, so it doesn't check. So with an even root function, you must remember to check your solution to make sure it's not extraneous. So letter A, again, was an odd root, so we don't have to worry about that. Letter C, that's a rational function. We'll actually use cross multiplication to solve there. But letter D, because it's a square root function, we do want to make sure that we check our answer to make sure it actually works. So let's take a look at number 10. I'm going to solve this by reversing my order of operations. So normally I would do my addition and subtraction last, but because I'm trying to undo what happened to x, I'm going to do that first. So we have the square root of x minus 3, and when I subtract 6 from both sides, I'm going to get -2. The next thing I can do to undo the cube root is to raise this to the 3rd power, and I need to raise both sides to the 3rd power. That way my cube root and my 3rd power undo each other, and I'm left with x minus 3. Don't forget, when you're cubing a number, you're going to carry the negative with it too. So ultimately, -2 times -2 times -2 is going to give me -8. And if I add 3 to both sides, I get that x is equal to -5. In letter B, the goal is to isolate the term that involves x. Then I'm going to do that again by reversing my order of operations. So I'm going to subtract 5 first, and I'm going to get 2 times x to the 2/3 is equal to 32. Next thing I need to do is get rid of this 2. Since I'm multiplying, I can divide both sides by 2. and I get x to the 2/3 is equal to 16. But I also need to get rid of that 2/3 power. That means I'm raising x to the second power and I'm taking the cube root. And I need to undo both of those. So I need to be able to undo my cube root by raising it to the third power. And I need to undo my square by taking the square root. So I'm raising both sides to the 3/2 power. And when I do that, my exponents are going to cancel and I'm going to be left with x equals. Now I got to think about what is 16 to the 3/2. Well, let's do the root first. The square root of 16 is 4, and if I raise 4 to the third power, I get 64. But I do need to remember, since it started off as an even power, I've got to include plus or minus in my final answer. Okay. In letter C, this is a rational function or a rational equation. We've got 2 over x minus 3 is equal to 5 over x. The way we solve these equations is to cross multiply. So I'm going to do 2 times x is equal to 5 times x minus 3. And now it becomes a linear equation. This is something you guys did in Algebra 1. I can go ahead and distribute that 5, and I get 5x minus 15 is equal to 2x. I'm going to go ahead and just move my 5 over to the other side by subtracting 5x from both sides. And I get negative 3x is equal to negative 15. If I divide both sides by negative 3, I get that x is equal to 5. And this is another one you can check. If I have 2 over 5 minus 3, I get 2 over 2, which is equal to 1. And if I look at the other side, 5 over 5 is also equal to 1. And so that means that both sides are equivalent. I know that's the correct answer. In letter D, the quantity that involves x is already isolated. So if I want to undo my square root, I'm going to square both sides. Make sure you put the negative 4 in parentheses before you square it. So the square and the square root undo each other. I have 3x plus 1, and that's going to equal 16. If I subtract 1, I get that 3x equals 15. And if I divide by 3, I get that x is equal to 5. But this is one we said we have to check because it's an even root. It's possible that 5 is an extraneous solution. So what I'm going to do is I'm going to plug the 5 in. I'm going to see what happens if I take the square root of 3 times 5 plus 1. Well, I know 3 times 5 is 15. And now I'm looking at the square root of 16. And the square root of 16 is 4. I'm trying to see if it's equal to negative 4. And the answer is no, it's not. So x equals 5 is not a solution. Or I can say it's an extraneous solution. How about that? But you might see the word extraneous. So it actually means that there is no solution to this equation. Okay. So in the second video, I will do the calculator section. But for now, we'll go ahead and close with part 1 of the final exam review.